this session, I'll be covering the basics of advanced driving assistance systems with few examples and a case study with respect to camera-based driver monitoring system. And I'll brief you through the process model in the automotive industry, which will give you an idea of the different kinds of the example systems are okay. The example systems would be like a simple rear camera, which will help the driver to see the rear view when the vehicle is operating in reverse gear, and the surround vision system, which will help the driver to see the different views without the usage of the mirrors inside. I mean, say for example, if he wants to, or if any additional systems like trailer of the vehicle is connected. I mean, if he wants to see the view inside the trailer, then different cameras that are positioned in the vehicle are used, and they are connected to the surround vision ECU. That ECU is basically the control unit that interfaces with all the cameras and then provides the view of the vehicle that is requested by the driver. And then driver monitoring system. Driver monitoring system is a safety system that is available inside the cockpit of the vehicle that will warn or alert the driver when the driving conditions are not proper. If he is not sufficiently active or alert, then it will slow down the vehicle or take any necessary actions so that the driver will be alerted and the accidents or any mishaps will be avoided. And lane departure warning is, I mean, if the driver tries to steer off from the lane discipline that he needs to follow, then a warning will be given by a lane departure warning system, so that the driver is alerted that he is not following the proper lane discipline. And traffic sign recognition is a camera-based system that detects the traffic sign and then alerts the driver if in case he needs to slow down or drive at higher speed if necessary. And adaptive cruise control is a system that enables a driver to set a particular speed as well as the distance from the vehicles that are moving in front and also from the rear. And speed limiter. And the speed limiter is a system that enables a driver to set a speed limit, so that if he's driving in highways which have speed limits for different sections, so that he will not be making any traffic violations unintentionally. So, and multi-domain controllers. These are the most recent or advanced systems for ADAS. So multi-domain controllers basically they have multiple sensors like cameras, lidars, radars, and the information or the data from these different sensors will be combined together to perform object detection, recognition, and then which are used by the algorithms to compute self-driving applications. So any questions in this? Basically, the recent trend in ADAS is the autonomous driving system. So we have automotive industry, I mean, Society of Automotive Engineers has defined 5 levels of autonomous driving systems. Like level 0, which is a current one, which does not have any automation except the cruise control and the speed limiter. So just the cruise control and speed limiter are the systems that enable the driver to set a particular speed or a speed limit, and with minimal driving effort. So the driving parameters are achieved with safety. So level 1 is a driving assistance systems with adaptive cruise control. So adaptive cruise control ensures that you maintain a safe distance and at whatever speed you drive, using radars and cameras, so that and also it enables automatic emergency braking, so that when the driver needs to slow down when the vehicle in front also slows down. And the lane keeping assistance, as I said earlier, it will be helping the driver to maintain the lane discipline. And the model that has this system is the Toyota Corolla. I think some of you might have seen this, and Nissan Sentra. So these vehicles have this level 1 autonomous driving systems. And level 2 is a partial autonomous driving, where the driver has to keep the hands on the wheel and be alert and ready to take control at any moment. But the steering and the speed of the vehicle will be controlled by the system. And it also provides the features that level 0 and level 1 systems provide. And level 3 is the conditional autonomous systems. So this is a recent trend that most of the OEMs like BMW and Mercedes-Benz are working on. This level 3 autonomous systems. So we are yet to start working on level 4 and level 5. So level 3 is expected to hit the market by next year, 2021. And so with certain driving conditions like limited access divided highways, like there are some highways which have certain driving conditions and which are mostly ideal. So these systems will be able to drive the vehicle with very minimal interference of the driver. But still, driver is required to sit behind the wheels to take over when the conditions are getting away from ideal. And the next generation Audi A8 is expected to be the first one to market with a level 3 autonomous driving system. And level 4 autonomous vehicles can drive themselves without human interactions. Like it is a robo-taxi. The best example is a robo-taxi fleet, which will be having a teleoperation and fleet control center. It will be like say 50 to 100 vehicles that will be entering the roads of the city with a control center, and then the consumer will be able to enter the vehicle, and then will be able to enter the vehicle and enter its destination, and then with restricted to known use case, with certain routes it can take, and then it can pick up and drop the customer with the known use cases. Though it's not completely implemented, there are two companies which are involved in this level 4 autonomous vehicles, like Nutonomy from Singapore and Waymo in United States. These two companies are trying to implement this robo-taxi fleet for Uber, for the taxi operator company called Uber. But the process is still on. The development activities are still on, and we are not sure when these kind of robo taxis will be into operation. And level 5 autonomous vehicles should be able to monitor and maneuver through all possible road conditions and no human interactions whatsoever. So these are, this is something like the individual customers will be able to get autonomous driving vehicles without a teleoperation and fleet control center, which is far ahead. So these vehicles will not require any human interaction in all possible conditions. It will be able to drive without any human interaction. So these are the levels of autonomous driving systems. And if you see state-of-the-art ADAS systems, they basically almost all the autonomous driving technologies will be using all these four sensors and five and a multi-domain controller, which will be having the capability to pick up the data from all these 4 sensors, and then pick up all these 4 sensors and then compute the data, and then compute the data and calculate the vehicle trajectory based on, trajectory as in at what speed and what steering angle the vehicle is going to operate. That is basically the vehicle trajectory. So the sensor data, camera is a vision sensor that will capture the image and send it to capture the image or the video stream, and send it to the multi-domain controller unit for vision processing applications. And LiDAR is basically a laser-based detection and ranging. I mean, it not only identifies, I mean, creates a 3D recognition of the object, but it also calculates calculates a range, that is a distance between the vehicle and another moving object, because as it sends high-speed laser pulses to perform object recognition and detection and ranging. And the top supplier for cameras and vision control units is Valeo, and the top supplier for LiDAR and LiDAR ECUs. Usually the sensors and the sensor control units are given by the supplier together. And if in case some OEMs will be requesting only for cameras, in that case Valeo provides only cameras, and then some OEMs will be requesting the surround vision system which will consist of both cameras as well as the control units. And the short range and the top supplier for LiDAR and LiDAR ECUs, Magna International. And the short range radar and short range radar ECU, I mean, basically they are ultrasonic radars which will be used for low speed maneuver applications for parking assistance systems. Say for example, if you have any obstacle while you are parking, there will be an alert sound during parking assistance, during the deployment of the parking assistance system. And long range radar is usually employed by the adaptive cruise control to make sure that the system maintains a proper speed and distance depending on the surrounding vehicles and the objects. And the top suppliers for radars are Aptiv, Valeo, Continental Automotive, and Magna International. And multi-domain controllers for vehicle control applications, the top supplier is Aptiv. So I'll be focusing more on, because I mean, we cannot cover everything in the same session. So I'll be focusing more on cameras and vision control units. So you can see camera, and this is an example of an automotive camera for automotive application. And then this ECU which will interface with the automotive with the camera, and then it will be providing the vision, providing the necessary view that is requested by the driver. So these are the applications of camera systems. So this is a rear view for parking and reverse. That's a rear camera will be placed on the back side of the vehicle, and there's a standard that is defined by Federal Motor Vehicle Safety Standards Organization US that mandates the rear camera presence in all the vehicles, so that when the vehicle is taken, when the vehicle is operated in the reverse gear, the rear view will be automatically enabled, so that the driver is safe, so that driver and the vehicle are safe, so that he'll be able to see the rear view without the help of mirror and any blind spots. And surround view is basically it can contain either 4 cameras or 6 camera systems, 6 cameras, where cameras are placed in the mirror position of the right and left, and the front and rear, and inside the cockpit, as well as if there's a driver monitoring system, there will be a camera inside the cockpit, and then camera for the trailer applications. And driver monitoring using cockpit cameras. Driver monitoring using cockpit cameras is basically, and since cockpit is a low lighted zone, mostly the light inside the cockpit will be less. Cameras that are capable of operating in infrared, zone are usually deployed inside the cockpit for driver monitoring systems. So the cameras will be monitoring the driver and providing input to the DMS, that is driver monitoring system ECU, and it will be alerting the driver by interfacing with the cockpit controller to give alerts or provide messages to the other control units to take safety actions for the vehicle. Triggered video record. Triggered video record is basically if you want to record the video of any view, that is, if you want to record the video of the rear view or the side view or the front view or the surround view, you can enable this triggered video record, and it gets recorded to the memory, recorded to the memory of the attached memory through the USB port of the vision control unit. And lane sensing and pedestrian detection warning, or the lane sensing and pedestrian detection warning are the systems that that will alert the driver when the lane discipline is not properly followed, and if any pedestrians are detected who are very close to the vehicle when the vehicle is moving. So these are some of the applications of the camera systems. So what I'll do is I'll present you a case study of the driver monitoring system, which will go through how we generally go about the designing of how generally the systems are designed, and then how the architecture is brought up, and how the components are chosen to meet the requirements of the customer or the OEM, and then how system safety, performance, and security features are enabled. Security features are enabled so that the driver monitoring system is meeting the requirements of the customer. So I mean, usually when the product is defined by the customer, the customer defines the product requirements at a very high level. That is, it is defined only at a functional level. Like the customer will define the functional aspects of the system. So these are the four example requirements that will be defined by the customer. So the driver monitoring system shall monitor the driver behavior continuously during the vehicle runtime. Means when the driver enters the vehicle and then switches on the ignition of the car, and the engine starts running, so the driver monitoring system should be able to wake up and then start monitoring the driver behavior continuously. So this driver monitoring system shall classify and report the drowsiness and gaze behavior. So drowsiness is a measure of the alertness, the lack of alertness of the driver. Is a measure of the lack of alertness of the driver, and so that the system either slows down the vehicle if he is very alert, and if he is very drowsy, so that there's a possibility of any accident, and or in case if he is mildly drowsy, then the vehicle will be giving a beep to make sure that the driver is being alerted. And gaze is actually detecting the eye motion of the vehicle driver, so that the system will understand that the driver is not properly focusing on the lane in which he is driving, and there is a possibility of an accident if he is continuously doing it for a longer duration of time. So that the driver monitoring system usually monitors these two parameters, and then it communicates the analysis to the cockpit controller, and the cockpit in the form of CAN messages, and then the cockpit controller triggers alert mechanisms like alarms to warn the driver, beep sounds to warn the driver, and in case of high risk, it controls speed. It controls the speed of the vehicle through cockpit controller. And the driver monitoring system firmware updates is, basically it is a programming as the OEMs, if in case they want to perform a firmware or software update, because the vehicles will be exported and exported and be used in different locations. So a callback of vehicles is usually very expensive. So nowadays OEMs are doing like mobile phones. OEMs are planning to update the software firmware through over the air. That's a recent technology where the software update is done over the air. Like that, the drive monitoring system will receive the firmware update similar to a mobile phone, and then it will be performing the update on them on reception. And the driver monitoring system should be able to record the driver behavior data on detection of abnormalities, and the data can be used for further analytics. So that the statistics of if the statistics of the data of the driver behavior data is available for a particular duration of time, then it will be easy for the analysis of the driver behavior, so that any correction measures can be taken after learning. So this is the drive monitoring system design at a high level, where there will be a cockpit controller, and then I mean the vehicle battery unit is the one that provides power to the DMS ECU, and then a camera is a sensor which collects the driver behavior data in the form of LVDS. LVDS is actually a low voltage differential signaling. That is a video format where the video data pixels are transmitted from the cameras to the ECU. I2C is back channel communication, is a connection between the DMS ECU and the camera. DMS ECU and the camera, where the diagnostic commands or the control or certain control commands are sent from the ECU, are sent from the ECU to the camera, for performing certain diagnostics applications. And the central gateway is usually nowadays the vehicles are very complex, and different control units will be having different communication techniques. I mean, some ECUs will be having Ethernet as their communication interface, and some ECUs will be having the CAN network as their communication, and some will be having FlexRay. So these are the communication protocols. So a central gateway ECU is a central ECU that sits in the vehicle that interfaces with different ECUs in whatever communication mode they want to communicate. They can communicate with the central gateway ECU, so that usually the flash programming is done through the central gateway ECU, so that it will have a common vehicle network to the programming tool. So they will be having an interface, CAN or Ethernet or FlexRay interface communication channel with the central gateway ECU. And any system will be having inputs, and without inputs you cannot process the data and the surroundings. So for cameras, you need, if they are operating in the visible spectrum, you need light in the visible spectrum, or the infrared light. If infrared light, if it's operating in the dark zone. So since cockpit is usually a low lighted zone, what usually we employ the cameras that can operate, that are capable of operating the infrared spectrum. So when we have an LED array power supply that have a light dependent resistor, which will switch on the operational amplifier when the light goes below a particular level, so that even if it is dark, the camera should be able to capture the infrared illumination that is reflected from the driver's face and the objects around, so that it will be able to form the image of the driver and analyze the driver behavior and generate necessary data that needs to be provided to the DMS ECU for analysis purposes. So we use the infrared LED array, which is generally employed to generate infrared rays in case the light is below a particular level where the visible spectrum cannot be employed to generate necessary driver behavior data.